In this lecture, I will introduce the use of the LCD display that is built into the Explorer 8 trainer board in conjunction with a PIC 16F1719 microcontroller. LCDs are used in a variety of industrial applications. They're very useful to be able to display text, special characters, numeric information, and they're very common in a lot of things that we see in our day-to-day life. So you might see scrolling displays on a vending machine saying buy an ice cold whatever your favorite beverage happens to be. You see these kind of displays on gas pumps and really just anywhere where some textual information that is sometimes alphanumeric needs to be displayed alongside some basic symbols. LCDs can accept commands and data. So the commands tell it how it's going to operate. So they can control things like whether or not a backlight is turned on, whether you're scrolling the text or just leaving it static, clearing out the current contents on the display, and moving the cursor position. Sending data actually sends what the next characters are on the display. So these next several slides have some screen captures from the datasheet. And so as we go through this lecture, I want to unpack some of the things that we can find out about our LCD module and how it's connected on the Explorer 8 trainer board from the datasheet. So this is from one of the datasheets for the LCM S01602DTR/M. And I have posted this datasheet on Canvas for those of you who are enrolled in my course. You can see that. But just to talk about what we see here, this showcases some of the mechanical dimensions of things and the spacing of our characters. As you can see here, our LCD can handle 2 lines of text, and it can handle up to 16 characters per line. And as you can see down here, each of these rectangles, each of these 16 characters, is comprised of a dot matrix display. And so the various letters, numbers, special characters that you can see displayed on there are made by using a dot pattern within this particular grid. So we have a 5 by 8 grid of dots, and that is used to display the various characters. Later on in this video lecture, I will showcase what characters can be displayed on the LCD and how to represent them. The pins on the LCD have several purposes. We, of course, just like most any electronic device, need a power and a ground reference. So that is what the VDD is, your 5-volt power, the VSS is your ground, and then V0 is for the LCD drive, and so that largely turns on some of the contrast there, and that is provided through a voltage divider. Then we have other pins on there, RS, RW, and E. RS determines whether what you're sending to the LCD at any given moment is instruction or is data. So if you're telling it to clear the display, you're determining whether the cursor is on or off or blinking, that is a command. That is an instruction. If you are sending the next character, then RS would be high here, and that is indicating the next character that you want to be displayed. You can actually read or write from this display. However, on the Explorer 8 board, this is hardwired to writing only. We cannot read anything back from the display. We are hardwired into simply doing a data write. And then E here is known as our enable. That is actually the clock. And so everything that is associated with this LCD is all about some sequential logic. And so you set up the command or the data that you want on these inputs DB0 through DB7, and then once that's ready, you tell it whether or not it's an instruction or data, and then you clock it on in. And so we will talk about how that is done on the Explorer 8 board in conjunction with our PIC in just a moment. But that's the basic structure of almost any LCD module you're going to see, is you have some instructions to come in or some data, and then you're telling it whether it's instructions or data using your RS pen, and then you're telling it that you're writing it using the RW pin, and then you have an enable, which is looking for an edge. So you're setting an edge, a low to high transition, in this case clocks in the next instruction or the next data. So, as mentioned, just to summarize, RS is used to distinguish whether we're talking about instructions or data. RW distinguishes whether we're reading or writing, and the enable pin is the clock, and our data and instruction come in on an 8-bit register, DB0 through DB7. Now, this is not the same as port D or port B. Do not be confused as to how those are connected. We'll talk about the hardware in just a moment. So this shows the connection. So as you see, this is the schematic for the LCD itself. And so we have the E, RW, RS. As I mentioned, this RW is hardwired straight to ground. So that is always in write mode. You have this VDD here connected to the positive 5 volts, VSS connected to ground, and then V0 is established using this voltage divider. That sets up the contrast ratio on the display. The E and the RS, along with our instructions or data, are actually coming from an external chip. So what we are doing with our Explorer 8 board is we are actually connecting some of the pins, as you see here, RC3, RC5, RA2, and RB5, just 4 pins, to this external chip. And this external chip is basically an I/O expander. And so if you had a limited number of pins and you wanted to connect to a lot of external devices, what you can do, as you see here, is use simply 4 pins to be able to control 10 different pins of output. So this allows us to conserve by using this. Certainly with a 40-pin microcontroller, we could directly control E, RS, RW, and the data lines. And in fact, in previous semesters when I used a different trainer board with this class, that was exactly what we did. We used some pins on port A to control E, RS, and RW, and then we used port D to control the data. However, the Explorer 8 board has a very different setup using this MCP23S17. The datasheet for that chip is also available on Canvas, and you can easily find that through a Google search as well. And so what this is effectively doing is it's using serial communication to set up what we have for our data or instruction and what we have for our E and our RS. And so it's using serial communication where RC3 here is the serial clock and RC5 is set up as the serial input. RA2 is used as the chip select, and so this enables using this chip at all. And then RB5 is a reset. So with that we can clear out all of the contents. And effectively what we're doing here is using a shift register to shift in all of the entries here for 2 different ports. This is effectively creating a port A and a port B. Port A, these 2 pins are controlling the E and the RS that we need for instructions or data and the clock. And then port B here, the GPB port, is our either data or instruction that we're using at any given time. So, in order to program things, we need to make sure we understand where these signals are coming from. And so the RW pin is always set for writing. We cannot, in this configuration, use it for reading. As mentioned previously, VDD, VSS, and VO are already hardwired, and our RS, E, and our various DB pins are provided through this external expander. And as mentioned, the CS line is controlled by RA2, the serial clock by RC3, the serial input by RC5, and then that reset by RB5. And the data commands, RS, are all sent in using the SPI interface, which uses serial communication. We'll talk a lot more about serial communication later in the course, but I just want you to be aware that that is how this information is coming in. We're clocking in 1 bit at a time until all of those registers are set up. There is a fairly limited instruction set for the LCD. These are instructions in terms of not the C code necessarily that we're going to be rewriting, but what needs to be set up on our instruction port, and then what would we put in RS and RW in order to clock in these various instructions. And so we will be using C code in order to provide these, but largely we have to set these up as voltages on the pins using our external I/O expander. And so as you see here, we can clear out the display. This is just going to take any characters that are on the display and overwrite them with a 20 hexadecimal, which is ASCII for space. And so effectively this just overwrites everything that is in the DD-RAM. The DD-RAM is basically just keeping track of what's in each character position on the display. And so this puts a space in there which just blanks out the LCD. We can return home, and so this sets the DD-RAM address, which is where we are actually going to start writing, to the top left position. We can set up entry mode, and so with entry mode this can determine basically how things are shifting and how our cursor moves. So our display is designed to be an international display, and so it can be used to display English words and various other languages, and some languages are read left to right just like we normally do, some are read right to left, and so you can actually determine whether you're going to move from left to right or right to left, and you can determine whether you're going to have a shifting of the whole display. With the display on-off control, you can actually determine whether you want a cursor to be displayed and if you want it to blink, so that's a personal preference. Sometimes you may just want letters and numbers to appear, other times you may want to see exactly where the cursor is positioned and have some blinking. That's in many cases just a personal preference. And then you see some of these other commands as you're going through. We'll talk a little bit more about those in a future slide about the function set and the cursor. And then down here, this is when we're actually writing data. And so our data that we're going to send in is going to be on these pins here. That's coming off of our I/O expander. And then for this one, the RS needs to be set. For every other one, which is an instruction, the RS is actually cleared. So these are the characters that can actually be displayed, and you can find a lot of this from a standard ASCII chart. So mostly we're going to be dealing with these last few columns here. You can put out special characters, you can put out numbers, you can put out uppercase and lowercase letters. And so this shows you what those actually look like in that dot matrix display. And so these are largely going to be coming from their ASCII representation. So for example, 0 is 30 hexadecimals. So this represents the first hexadecimal digit, this represents the last hexadecimal digit. So if you wanted to write displayable 0 out, then you would send in 30 hex. If you wanted to send the letter capital R here, you would send 62 hexadecimal. As you can see over here, this even expands to put out various Asian characters. You have some special symbols like the cent symbol and things like that. This we'll use later when we get into a temperature lab for the degree symbol. And so we also have some of these mathematics symbols available as well. The initialization sequence needs to be done in a very particular order. So the first thing you need to do is apply power. So the LCD panel needs to be powered on. And then you have to wait for at least 30 milliseconds after the powered voltage rises to 4.5 volts. This will largely not be an issue because as soon as things power on, you're going to be not running your code immediately. There will be some other setups that will happen, but once you start talking to the LCD, these are the things you need to do. The first thing is a function set, and so with that you're setting it up for 8-bit mode. So this LCD can actually be programmed with either 4-bit or 8-bit instructions. 8-bit instructions is what we're using because we're using this I/O expander, which allows us to put out all 8 bits at a time. 4-bit mode is also commonly used with LCDs, and largely it means you have to send one nibble at a time rather than the entire byte of command or data. and this is used for saving pins. So if you were trying to minimize the number of pins that you're using on your microcontroller, if you had a very small microcontroller, you could send this out one nibble at a time. But since we have the luxury of this external chip, we are going to be working in 8-bit mode. So that's already a solid 1 in there. If you want to, you can choose to either use just one single line or 2 lines. We're going to be using predominantly 2-line mode, so you see that as the N here in the function set. And we want to just turn our display on, and so we'll have that for both our F and our D values in here. And then whether or not you have the cursor on or you're blinking, that's really just a personal preference. You may have some different instructions depending upon the lab assignment or in-class exercise that I give you. And then we're largely going to be dealing with increment mode, which means we're going to be incrementing to the next position in RAM, which moves us every time we put a character to the next character to the right. And then the SH is whether you want to have the entire shift on or off. So this is basically if you put out text and it fills up all 16 characters on a line, and then you continue, do you want to just shift everything over so you can continue to display the next character that comes in? So the sequence of execution for the LCD, if you're sending in an instruction, you want to set up the instruction. That's going to come in the external chip, and also on the external chip you're going to clear the RS and you're going to clear E, and then what's going to happen is after a delay you're going to shift in another set of values, and that's really just going to change E to a low. To a high. So you'll have a low E and then a high. That rising edge on E is what clocks in the instruction. If you're sending in data, it's very similar, except you're setting the RS to indicate that it's data rather than instruction. But the rest of the procedure is essentially the same. The LCD can only display 16 characters at a time on each line, but it can hold more than that in memory, and so if you're scrolling, those things can be stored such that even though they may not be on the display at any given moment in time, they are stored in memory and can scroll. And so you see the memory locations on there. If you're operating in single line mode, you have between 0 and 4F hex. If you're operating in 2-line mode, then 0 through 27 hex is the top line, 40 through 67 hex is the second line. The MCC, which is the MPLAB code configurator, actually knows about our LCD, knows about our external chip that is used to help write to the LCD, and you can actually automatically create functions that can be used with the LCD. These functions were actually provided in the first lab that we did this semester in LCD.H and LCD.C. And so I will, in class, explain these in more detail. But we have these functions available which automatically take care of a lot of the things that we would want to do with the LCD. The LCD initialize goes through that initialization sequence, setting up things like the cursor mode, input mode, make sure everything is set up so we can send data in there, clears the LCD out. We have write IO expander, which allows us to write out to the registers on that IO expander so we can set up things like our RS, our RW, and our E. We have write command to write out an instruction, and write byte to write out data. We can write out an entire string, and that just goes through the write byte until we get to a 0, which means we have what's known as a null terminated string. And then we have goTo, which allows us to position the cursor on a particular row in a particular column. And then finally we have LCD clear, which allows us to simply clear out the entire display and put our cursor back in the home position, which is back at the top left. In class, I will go through the code in much more detail showing you this, but this just introduces you to the functions that are available to work with the LCD. And we will be using these functions in many future labs as we try to display information about sensors and other information on the display.